Hi there, I'm Blair Johnson, and in this talk I'm going to address meta-analytic models of effect sizes. This is an overview. It's not into the nitty-gritty, but just to give you a big picture of it. And here's the big picture. So I like to think of meta-analysis as broken into 7 steps. Most meta-analysts probably just do steps 1 through 6. They don't bother reanalyzing, but it does increasingly happen. So in this modern world, I like to think of meta-analysis steps as highly integrated. You formulate a research problem thinking of the whole process that follows. The better you do each step, the better each one that follows will proceed. Sometimes you learn in the process that you need to redo something. So you might have to go back to an earlier step and redo part of it. But at this point, you've done all of these steps. Let's assume that you've gotten all the way to step 5. You've got a database from your effect sizes and all the things that you've coded in the studies. You are ready to analyze. So in this talk, I've got these big picture points first, just one slide on the big picture to orient you. You can look at my other talks to see other discussions of the preceding steps. Most of this talk, as you can see by the number of slides that I'm going to present, is going to be on classical meta-analysis. In the last 5 or 10 years, it's become very conventional to call just a simple fixed or random effects model of effect sizes with only one outcome per study as classical meta-analysis. We do have the problem in meta-analysis of dependencies among effect sizes. So, and I'll explain different ways that can happen. People giving different measures in the same studies, comparing a control group more than once, and so on. So I have a few slides about that. Again, just a basic introduction. And then I'll leave you with a few discussion questions at the very end. Now, this talk will not directly address moderators, although at certain times I'll imply it. If you're interested in effect modifiers or meta-regression, as we often call it, my own talk on that is maybe starting to get dated, but not so much, mostly. Everything I talk about in this talk, which you can reach at this YouTube address or the QR code that you have right here, most of the meta-regression strategies that are in this talk generalize to the more modern dependent effect size analysis too, even though I don't talk about it in that talk. So I recommend that as a place to go to look at moderators. And if you want the paper for that one, which this talk is literally showing you how you use what I call the moving constant technique, then there's the paper that goes to the public version of that article. Moving constant technique is a way to make sense of more parts of the model than most analysts tend to use. So highly recommended, and students in my seminar learn how to do that, so take note. Now let's get into the classical meta-analysis side of things, and these are going to be simple models of effect sizes. Mostly we're just looking at mean effect sizes here. What are the necessary statistical ingredients? Well, you're going to need an effect size in one form. Often in these analyses, when statisticians talk about effect sizes, usually we start talking about T as a generic form of effect size. But in fact, you're going to need one form of them only. You don't mix effect size outcomes in the same analysis. That would be crazy. The standardized mean difference would be one. The log odds ratio would be another. Fisher's transformation of R and transferring it back to R for interpretation purposes. Arithmetic means, and so on. All of these are forms of effect size that you can model as T's. And then you need an inverse variance for each effect size, or you need a standard error. Some software uses the SE instead of the inverse variance. And those define the weights for analyses. So in classical meta-analysis, I've already said, you have only one effect size per study or portion of studies. And sometimes you disaggregate studies for moderation purposes, as I've discussed in previous talks. Lipsy and Wilson gave a nice compact description of a whole bunch of effect size statistics, types of effect sizes. So you've got the stats, you've got the standard errors, and you've got the inverse variances all defined there. And I like to tell people, if you want to get an intuitive sense of these things, especially for the standard error or inverse variance, especially look at the correlation case. You can see that the inverse variance is basically the sample size of a study for a correlation. So anyway, these are the basic ingredients. And then you're going to go off and analyze the meta-analytic database. So usually, and I'm going to show you one in a little while, so bear with me. Usually with classical, formally, really, this is the only way to do it with classical meta-analysis. You analyze within an outcome variable. If you have multiple outcomes, you'll just restrict your analysis to one outcome at a time. You'll conduct homogeneity analysis, sometimes labeled heterogeneity. You're going to inspect for strong outliers, mindful of plan analysis. I'm going to give you an example of one in a second. And, well, maybe less so on the second side of that, mindful of plan analyses. But I mean, you can see what I'm doing is I'm telling you there that, well, you might see outliers when you look at overall effect size databases, but maybe they're outliers because of moderators that you're going to examine. So keep this in mind. You could inspect for publication bias, but there's, again, a case where I'll refer you to a separate talk. So for today, we're going to ignore that. So the Pearson product moment R looks like that, and the transformation, Fisher's transformation, is given here. The standard error looks like that, and the inverse variance looks like that. So as I said before, the weight in analyses is very intuitive when you think about R. And it should be noted that the R also has its own little bias. So people who get all sanctimonious about R being purer than the standardized mean difference, not so much the case. In the case of the standardized mean difference, you've got equations that look like this. The standard error and the inverse variance. These are much more complicated than the R formula, and as I've discussed in previous talks, they actually include the effect size as part of the weights. So this is a little weird, but that's the way they work. Okay. Now, you could even do models of standard deviations across the literature. Several years ago, we needed to know what the typical standard deviation is in a trial of physical activity that focuses on blood pressure. And so this is 334 different trials focused on physical activity in various populations. We comprise these across 3 or 4 meta-analyses we had done at that point. And I've just plotted, and this figure on the x-axis is the observed standard deviation, and the y is just a sample size thing. And this is really the way you should see a distribution look. It should look very normal. And I suppose we could even go out and apply statistics for that if we wanted. But for this, it gets complicated with standard deviations because they're a different beast, and there aren't a lot of meta-analyses of standard deviations. I mean, here's one. I throw that out to people if you're interested in this problem. We could play around with it. So back up just a second. When you get your blood pressure checked, it's 120 over 80 or something like that. The 120 is the systolic blood pressure, and the 80 would be the diastolic. So here's SBP, and so usually you see SBP is a little higher on a standard deviation, and in terms of its value, and DBP is almost always lower. Here are the same studies' estimates of the standard deviation of diastolic blood pressure, and that looks a little weird, doesn't it? We've got this funky case down here that just does not belong. So here is the first example that I've recorded of an outlier, and probably one that's artificial because, gosh, look at how far away it is from the distribution. So what do we do with outliers? An outlier might be telling the analyst that their theory is wrong. Now, what does the analyst do? Well, they might just erase it. Outlier. Wonderful wordplay. Beautiful. One of my favorite funnies. So here's the study in question. We want to look it up, and the SBP one, if you convert their statistics, which are mean plus the standard error of the mean, that converts to a normal looking standard deviation for that particular part of this, that's DBP, excuse me. Now here's the other subsample. It had only 27 people in that particular one, and that SEM of 23 translates into almost 120 standard deviation, which is what we saw in the previous figure. So that's bad. Okay. So maybe what happened is that they left out a decimal point. It should be 2.3 instead. If so, the standard deviation would look much more normal. Okay. And I'll go forward, not backwards. if we take the p-value over here, it implies a pooled standard deviation of 11.86 between these two groups. So again, it's squaring with this estimate that we just figured out here. So our guess is that this particular study was published and the authors blew it. They didn't catch a typo, or the typesetter screwed up somehow. We don't know. But in this case, it's completely correct to put in the value that we've estimated here. It's just missing a decimal point. So now we get rid of our liar and we show the figure again, and indeed it looks normal. So voila. But if you'd gone ahead with this distribution as it looks here with modeling, this case might well have some dramatic effects on your estimates, and so that's why we worry about outliers. Now, how does a database look when you're going to do a meta-analysis? You would probably have columns in there. I've got a UID column, which is for each line in the database. Each one has a unique number, so that's unique ID. Some people literally spell out unique ID as one word. ID in this particular definition in this particular database that we've designed is a study unique ID for our, so you can see that some studies have multiple effect sizes. Here's number 283 by Bukalu et al. Is in this database twice. This database is an intervention database. We're looking at HIV prevention. Just judging by the details over on the side, it looks as though this is probably the database that we compiled for HIV prevention for adolescents, but it doesn't really matter. We put in a citation column because, you know, your memory, you're really kind of bad at remembering what ID numbers or unique ID numbers. So why do you want to do that? And so having a spelled out citation name gives you a lot of information all at once. You can see sometimes studies are reported more than once because, look, that study was reported apparently 3 times, looking at different outcomes or what have you. So we're grouping them, we're giving them the strat. Well, we know that they're not independent from each other, and we've solved that problem in creating this database. The condition variable out here is telling you, well, like in Karan et al., we broke it out by 2 different samples. We've got one with seniors and one with juniors. So literally using the words of the intervention itself to define this, so it's easy. If you go back to look at it, you know what you're doing. This little variable out here in the end is measurement occasions. So they've reported that they've got a number of pre-test, post-test follow-ups, whatever. And then here's the stuff that's really salient for this particular analysis. So continuing on from there, after measurement occasion, it's just repeated it down below here. Now, I've coded whether this particular effect size is the first, and this one on top is not, but it is the last study that they looked at. This is my way of trying to look at, well, the first, how are effects looking at the very first available outcome? How are they looking at the last available one? How many weeks have elapsed between the intervention and the measures? And then after that's all effect size related information. Effect size 30 turns into D30 once you do the correction. You can see that the values are slightly smaller in this one. This first study is pretty big, almost 1,000 people. So the correction isn't very much. In fact, that one even rounds to the value we've got here for effect size 30. But if the next ones are much smaller and you see the corrections are bigger, that's the way it should be. We've got all the calculated weights. We've got a variance. We've got the weight, TW, that's the inverse variance. We've got the standard error in there also. Depending on which software we want to use for analysis, we might need any number of those. And then we've got just the basic information about the trial out here, and then on to the next effect size, D31. So if we go forward, now I've used very compact names to label these variables because in output, oftentimes they'll truncate them. It can be very confusing if you don't have short names. These are in Stata, so it likes to assume lowercase names. In fact, you can have the very same name, but one could have a capital letter starting it, for example. But those are different variables in Stata. And what I've done is to use a numeric strategy to differentiate between effect sizes. So in this example, D30 is condom use and D31 is sexual frequency and so on. We have a whole, well, as you can see, we've numbered up to 31. In fact, we have all the numbers before those. I think we also have a D32 in this database. And one advantage is some software is going to need you. I mean, this database that you've got in front of you is mostly wide. The variables are all strung out like the effect sizes for D31 and D30 would be these are standardized mean differences, and it might be in our plan to contrast those effect sizes against each other. If so, we can't do it with the data wide like this. Instead, we'd have to make them long. And so we'd make if you've numbered the variables like this way, in Stata at least, you can reshape databases so that you can now use the information more effectively. All right, so that's the and I'm not a big expert with R or some other software platforms, but basically go out and look at develop some knowledge about using that software and make sure that you name your variables in a way that's convenient for your system. So this takes us into formal statistics in the classical forms. You're going to have if we start out thinking of the simplest model, it's going to be a fixed effects model. And so you can imagine that the observed effect is equal to an actual effect plus some amount of error. Now, this is the way statisticians like to talk about it. Now, this model is going to assume that the variation you see across studies in the t-values that you're examining, it's only due to sampling error. Oops, I don't want to zoom there that much. I want to slide forward. I guess I have to zoom out enough to make it go forward. There we go. All right, finally. So each observed effect is approximately equal to each other effect all the way through till your last K study. And that is approximately equal to the population effect size. So Greek letter theta, capital theta. And then Q, which is distributed, is approximately x squared. Sometimes in the old literature, you might see it labeled H. That's a long story. But the convention has pretty much eliminated that. It's now called Q. It's distributed as approximate chi-square distribution with K minus 1 degrees of freedom. And it evaluates whether this is true. So if you have more than that, it's a poor fit, essentially. Now, in passing, I squared also does the same thing. And so does tau or tau squared. So don't miss that point. In fact, these are probably more, especially these two, are very important to report in your outcomes, in your reports of meta-analysis. So borrowing from Borenstein et al. For a few images, here's a way to think of fixed effects assumptions, is that they're all centered on the theta, the population value. So every study in theory is getting the very same effect. The problem is, in reality, that's not going to happen, right? They're going to vary somewhat. So in meta-analytic statistics, you have this kind of stuff going on. You've got weights multiplied by each individual effect size. You're going to divide the weights out at the end. So this way, studies that need more weight get it. And so the mean value will follow the ones that have the larger weights. And you can calculate a standard deviation by an equation like this. There's a standard deviation, effectively, of the inverse of the square root of the weights, the sum of the weights across the whole set of studies. And that will give you a confidence interval. And now if that confidence interval excludes the null value, the effect size is significant, the mean effect size. Okay. And here's how we evaluate the fit of them. It's essentially taking the mean from every individual observed one, multiplied by the weight, square those differences, multiply that by the weight, and that's distributed as a chi-squared, as we said before. Okay, so back to sampling error. Those studies that we have in reality are going to observe effects that deviate from the original. So that's what we're seeing in these cases. The true effect is 0.6, we're assuming, if we do a fixed effects model. But they're deviating. Okay? They shouldn't deviate any more than sampling error. Okay? So under random effects assumptions, we would assume that part of the observed variations beyond sampling error, and we're going to label it U, can be known from the observed distribution of those effect sizes, the so-called true variation. Statisticians say true, that doesn't mean that you've discovered the truth. It means you're thinking about the underlying effect in a little different way. You're imagining that part of that distribution that you're seeing in effect sizes it should be there beyond sampling error. Okay. So you use that when you want an overall model for effect size. So it would be T, usually we think T plus or T period as a mean symbolically. If you want a overall model for the mean and you have significant homogeneity statistics, then usually convention is favoring the random effects assumptions. Okay. So is that your only goal? I mean, if you have significant homogeneity statistics, it's telling you something is going on in your database. And so I would take you back to step one. What does your topics plus M definition specify? And especially focusing on M here because you probably have some operator expectations. So back to conceptualizing how these things look. You've got a distribution of true effects around a grand mean. So when you're going to random effects assumption, you're thinking about that mean as more like a mean of means, a meta-mean. Oh, and t squared, or tau squared, excuse me, would be the variance of the true effects. Okay? To the extent it's non-zero, and it can only go positive, obviously, as a variance, then there's variability in the population effects. Okay? And as a simple principle, if tau squared is equal to 0, then I squared is equal to 0 too. Q is not going to be significant. Okay? This is another way to conceptualize the random effects assumptions. The individual studies are assumed to be tapping slightly different things, maybe dramatically different things, hard to tell. And each of them is then going to be sampled from its own distribution of effects. And this is just, again, imagining what it would look like. And then the overall effects look more like that. You're just averaging the distribution. Again, a mean of means, distributions of distributions. So I guess you could say that random effects assumptions are more meta than our fixed effects assumptions. Fixed effects assumptions are very simple. Okay, so here's another example of a forest plot. These are real data. If I remember, exercise trials for cancer survivors, looking at what outcome was this, quality of life or something like that. And we've rank ordered them from the lowest benefit. None of them are significantly different from 0 to the biggest benefit, which is quite a large effect size, by the way. And so you get a snapshot of a literature this way. A lot of people call this a caterpillar plot because it resembles one. Caterpillars aren't really that useful for most meta-analyses, but for what it's worth. And you can diagnose different things from forest plots. Like you can see that the studies on top of this particular figure have smaller confidence intervals than do the ones at the bottom. Well, probably that's publication bias, but we'll talk about that another time. Right. One possible reason would be publication bias. Another one would be a moderator that happens to be correlated with sample size. You know, different type of cancer or something like that. So now let's think what happens when you weight on a fixed versus random effects basis. So here's a fixed effects model, and again borrowing from Borenstein et al. And you've got what, 6 different studies here. 2 of them reach significance. The other ones do not. And you can see the blocks are made bigger when you have larger studies. That means they're getting, and it says right here in the graph that that particular study has 39% of weight. And so the mean is going to pull in the direction of that particular study. Okay. Now here's random effects assumptions. And I'm going to erase the ink on my slide. Oops, what did I do here? I don't want to show you that all at once. Where am I here? Here. Now you can see that that one that was 39% is down to 23%. When you go to random effects weighting and meta-analysis, you get much closer to weighting each study equivalently. So it's another caution for you, perhaps. It means the studies that are very tiny are going to suddenly have a lot more weight. If we go back, look, the one with least was PEC, 8% on the fixed effects. When you switch over to random effects, it goes up to 13%. So that's what's happening here. Now the random effects mean is going to be much closer to the center of all of these, and you can see that in this example it's true. Okay. In an extreme version, you might see something like this. Look at Granger's 61% on the fixed effects version. And you know, the mean value is even lower than all the other effects that you see in the particular model. And try to move forward here. There's the random effects version, and the mean is moved back over to the right. So it's representing the studies much more equivalently. All right, so another way to conceptualize dispersion of results, here we've got all the statistics that we tend to see reported. And here's an example where Q is equal to 3, it's non-significant. And none of the other statistics differ from 0 either. It's homogeneous. Here's an example where Q is significant, and that implies that there's significant variation across the studies. They deviate more than sampling error. Now, one thing to notice here is people report tau squared and it looks like this. The values tend to be much smaller because the units for tau squared tend to be based on the type, they are based on the type of effect size you're looking at. And with the standardized mean difference like we got here, or maybe it's a correlation, either way, you're going to have a very tiny value for random effects variance. But if you report the standard deviation version, it's bigger. So here's a recommendation. Report this one. And they're equivalent statistics otherwise, so it doesn't really matter. But that also intuitively should give you a sense the standard deviation of the effects is 0.19. So wherever the mean is on this one, around here, I suppose, plus or minus that, it's going to probably, this one doesn't tell you if it's significant or not, but it might not be significant. Here's a larger example. It basically just doubles the first database, but essentially everything else is exactly the same. A and C are essentially equivalent meta-analyses, showing very consistently this effect size showing up across the study. And you see how this is not dependent on the number of cases, although the p-value could be something to keep in mind. Here's the first database, and see how, again, it's just basically just double the database. It's just multiplying it by itself. I squared is staying about the same. T is exactly the same. Or tau in this, I think it's just a font choice in this case, but usually you would say tau, the Greek letter tau instead of T. Anyway, it helps to show, oh yeah, one last point here. Look, the p-value for the Q associated with this second distribution, number D, letter D, is gotten much smaller than it was up here. So what we learn from this is Q is high and is highly dependent on K. So it's a caution for you if you got a small meta-analysis, you may not have enough power to detect differences across studies. You've got all these different measures of effect size dispersion, which I've already given you. So Q goes back to Cochrane 1954, even though he didn't label it that. The convention's pretty much taken that up with and labeled it for Cochrane's Q, but that's where it came from. So you've got a range of, this is important. Q is theoretically infinite in its distribution. There is no upper value for Q that limits Q. Of course, in practice, you're going to observe a non-infinite, a finite value of Q. So that's all well and fine. It, yes, does depend on K, the number of studies, and it does not depend on the effect size scales, and it's going to benefit that way. And if you're just looking at the p-value, all the same things are the same. All of those conclusions are the same. You're looking at tau squared and tau, of course, those are going to be the same because one is just the square of the other. So here's the variance version, and here's the standard deviation version. And this one is, again, theoretically infinite, although in practice we tend to see that tau square values are much, much smaller than that, or tau values. They don't depend on the number of studies, but they do depend on the scale used. So if you created a tau squared for, say, analysis of mean values that are based on POMP, tau squared will definitely go much, much larger than you tend to see with a standardized mean difference, where you tend to see mean effects around 0.5 or something. And then I squared has the benefit of not depending on the effect size scale. It doesn't literally depend, the value doesn't depend on K, but testing its significance does. Okay, so put a star by that one. And if you looked at I squared as a proportion, very same thing as with percentage. So I squared is usually, I would say, use the convention of expressing it in percentages rather than proportions, because it can confuse people if you report you've got an I squared of 0.94 and you don't tell people it's a proportion, they're going to assume I squared is really small. okay, because they're thinking in terms of percentages. Now, Higgins et al. Described 25, 50, and 75% values of I-squared as low, moderate, and high, okay, as a tentative adjective. But of course, like all things that are said this way, it caught on like a horse leaving the stable. So there you got it. And they even brought out some figures to show this. But anyway, you should keep in mind that these are arbitrary. And as I just told you, I didn't give you the derivation of I-squared in this talk, but it's based directly on Q. There's a simple equation for it. And Q, as we said, goes all the way to infinity. So in theory, 100 in I-squared would be equal to an infinite value of Q. Therefore, I-squared should never be 100 because, unless it rounds to 100. In fact, you can find very large values of I-squared, but they should never reach 100. So you're going to evaluate the statistical significance of those things. You've got the test of significance for Q or I-squared. If it is significant, the implication is that you should reject the hypothesis of homogeneity. In other words, here's how you would say it. The study results varied more than sampling error alone would predict. It's also telling you a fixed effects model is not that good. And it means that you've got an incorrectly specified model. Okay? So, as I said, small samples, you're less likely to reject the hypothesis of homogeneity. And literally, that is the hypothesis you're evaluating with Q or I-squared. It's the default, the zero value is what you're evaluating. It should be zero. Q should be non-significant. I-squared should be zero if the homogeneity hypothesis is going to be supported. Now that takes me to the last major part of this talk, which is what do you do with multiple reports from the same study? So you allow, and I'm going to describe this in a second, a little more detail. Do you allow each effect size to enter the analysis? Generally in classical meta, you shouldn't do that because we have the assumption of non-independence of observations. And so you shouldn't be doing that. Maybe there's some times where you have to. And just kind of a caution is that you might actually have multiple publications from the same database. You don't want to include them twice because they look slightly different from each other and you're treating them as different. Then you're literally allowing each observation from that particular study to enter multiple times. And you're going to skew the results toward that study, as I just showed you, like with fixed effects assumptions. And it just sometimes makes you wonder, meta-analysts are out there like the police, trying to detect when people are piecemeal publishing stuff. So we should all utilize responsible conduct of research. So I'm going to borrow a few slides from James Pustoszewski's at UW-Wisconsin. Excuse me, UW-Madison. Dependent variables, dependent effect sizes are very common. So you might have multiple measures from the very same participants. You've got depression, anxiety, whatever, stress, and the same study. And so you might have variables that you think of as related, and you want to examine all of them. You might have the same outcome measured at multiple follow-up times, and of course, a version of that would be doubling up on multiple outcomes. So if you've got multiple follow-ups, then you're going to have this problem showing up too. You could have multiple treatment conditions compared to a common control. So in this case, you've got T and U treatments, and you're going to compare them each against this mean value for the control. And so you'll get two effect sizes out of that. So the control people are showing up twice in this particular example. We haven't faced this too much so far in the series of talks and in class, but you can also have multiple correlations from a common sample. And so you've got all possible combinations, perhaps, of variables under interest. So, and there can be different combinations, as I've implied, for all of these things. So in fact, reality in the research world is that dependent effect sizes are extremely common. And here for decades, we've been following this classical model where we try to force our study results into this probably fairly artificial modeling. So Becker, back in 2000, described 4 broad strategies for handling dependence. So you could ignore them. You could ignore that's mostly what we've done in classical. If you could combine them, you could subclassify, and you could model, okay? So with more detail, so ignoring, we don't want to do that, right? You could combine the outcomes across everything observed in a study and just have one effect size for each. You could, actually there's another version, okay, yeah. You could subgroup the outcomes. So as I applied, we would do a classical meta-analysis. This is a way that we often deal with it. Cooper suggested a shifting unit of analysis one. You might have study level effects, you might have measure level effects, for example. Or you could model these things all at once. So Raudenbush and colleagues have looked at this, Gleiser and Olken have looked at this for quite a while, actually, but mostly these solutions have been difficult for people to put in. More recently, we've got multi-level meta-analysis, meta-SEM, so a structural equation modeling version of handling dependencies. And probably the most popular of these is robust variance estimation. So now we can go ahead and put all those effects into the very same model. Okay. So this is all from James, but RVEs, these are some reasons maybe why RVE has been popular, is that it is a very general class of models that it can work with, and so it's intuitively graspable for a lot of people. You can use it in combination with all kinds of working models, so and this way try to capture the structure of your database. And then this allows you to break out components of within and between study heterogeneity, which looks exactly like I just showed you for classical meta-analysis. And it appears that RVE is a good way to guide against model misspecification. So what we ought to be getting out of RVE is more trustworthy results. So, and so there are some cautions. I mean, well, the original versions especially were limited, sometimes sacrifice efficiency. So beware the solution you use when you go to invoke an RVE solution. Here are 3 of the common ways contrasted against each other. And I'm not going to belabor all of this, but there are some things to highlight. Like with multi-level analysis, at least so far, they're ignoring correlations between effects. So if we were looking at depression and anxiety outcomes and interventions, we'd expect them to be fairly substantially correlated. And if that's being ignored, I would be uncomfortable with that. So for me, I probably at this point would not use multi-level meta-analysis for that. I already said solutions with multivariate analysis, meta-analysis have tended to be hard to use. But at least it forces you to think about the correlations between estimates. And RVE, on the other hand, is making some working assumptions about effect size correlations. In fact, I've played with this myself. And it usually doesn't matter if you assume the correlation is 0.2 or 0.8 between outcomes. I'd be curious to find out what it is that makes that matter or not. And the claim here is that you do get some pretty robust inferences out of these models. So James says, why model? Because you can include everything in one coherent analysis. You can break things out within the study or between the study level, simultaneously, really. You can describe the heterogeneity of effects at those levels. You can assess uncertainty and average effect size estimates and meta-regression coefficient estimates. So it's friendly to go to meta-regressions, modeling effect sizes. Again, not the topic of this talk, but we'll come to that. And he makes the point as well, these things that you want to get out of the models depend on the modeling assumptions being correct. So, I mean, as a statistician, he's going to talk this way, that beware of being wrong on your models. Okay, now, if you want more information about that, James recently put down a YouTube video on exactly this subject. It's only a little over a half-hour long. So there's the YouTube link at the top, and this is a QR code to the very same spot. Work that he's doing with Tipton, who was one of the developers of RVE estimates for meta-analysis back in 2010. And they have a paper there you can go to download as well. So I'll leave you with a few discussion questions. What is the best model for effect sizes, fixed or random? And what are you getting if you do those things? And Eventually we'll talk about another version that you could label mixed effects, but that tends to be used when we get to moderator tests. What's the best way to handle dependencies between study outcomes? And I think you should ask yourself that for the meta-analysis you're doing. Does it matter for your particular literature, and how does that map onto your topic splits and your whole plan for the meta-analysis? And then finally, I'd say, well, what are the other forms of dependencies that might be important in meta-analysis? And I think that would be worth a good 10-minute chat. So I look forward to that. Have a great day.